Hello and a very warm welcome to another HAKOM webinar. I'm Stefan Komornyik, co-founder and managing partner at HAKOM Time Series. Like always, all our live webinars are recorded and uploaded to our YouTube channel. You will receive a direct link along with a follow-up email right afterwards. Check out our YouTube channel and hit the subscribe button to stay up to date on Time Series. Last time we talked about AI's power with a focus on time series management. We specially pointed out some exciting features of AI helping to generate synthetic data. Today we will address another hot topic, AI's hunger for energy. Among many papers currently published, one was specifically interesting. In an article in the Scientific American, the author Lauren Leffer put it like this. If you fully turn Google's search engine into something like ChatGPT and everyone used it this way, Google would need as much power as Ireland just to run its search engine. In a worst-case scenario, it is estimated that the global electricity consumption of data centers could tenfold, resulting in an incredible 10% of the entire global consumption. This naturally raises many questions. How exactly is the energy consumption for AI generated? What stage of using AI requires how much energy precisely? And in addition to those questions, one is paramount. What can we do to reduce this massive energy consumption? No wonder researchers at MIT's renowned Lincoln Laboratory are working on this problem already. In their in-house supercomputing center, they are looking into strategies of reducing AI's hunger for energy significantly without sacrificing anything. And as the lion's share of data analyzed in the energy industry's time series, there's reason enough for us as experts in time series management to take a closer look at this topic today. So, there's our agenda. We will discuss why AI is an essential component to build sustainable energy grids in the future. We will focus on the interplay of computing efficiency and power consumption. We will show how a native cloud service is set up and monitored easily. And we will get special insights how operators identify and analyze bottlenecks to optimize usage and quickly improve performance. With us is Clemens Wasner, co-founder of AI Austria and CEO of EnliteAI. Together with his team, he built a deep tech venture studio focused on the creation of AI products with the potential to be rolled out globally. He's very active in the Austrian AI community, publisher of the AI Landscape, and board member at the Adria AI Data Robotics Association. For the energy sector, they have developed an award-winning power grid management solution, solving problems of congestion management and grid control. Our second panelist is Christian Kornfeld, head of product development at HAKOM. Christian has been working in software development for 15 years with a focus on time series management right from the start of his career. Together with his team, Christian is constantly pushing the development and operation of PowerTSM, HAKOM's state-of-the-art cloud-based time series platform. So, let's meet the panelists and jump right in.
Everybody live now. Once more, welcome to our HAKOM webinar. From our speakers, Clemens, Christian, and myself. Hi. Thomas also joined, my co-founder and head of product management. He will join us during the Q&A session at the end. And I'm proud to say that we are more than 200 already. So thanks once more for your great support and commitment to our webinar series. When we started planning this webinar, we were aware that AI and computing efficiency is a real hot topic. It's just so relevant, especially for us, the tech in energy community. There's hardly any topic that could be more important. The fact that AI could represent up to 10% of global energy consumption, that certainly poses some questions that we urgently need to answer. Therefore, like always, I kindly ask you to ask your questions. There's the Q&A function, you know how it works. In our session at the end, we will try to answer everything you drop in. So please, once more, challenge us. Clemens, being a true AI enthusiast, please tell us more about what can we do to use AI for good in the face of its massive hunger for energy. Clemens, please go ahead.
Yeah, thanks a lot for the nice introduction words, Stefan. And yeah, also thanks to the colleagues of HAKOM for having me here today in this webinar. As was briefly already teased in the video before, I will give you a very brief overview how we are utilizing AI for power grid control. And before I do so, I would like to tell you why is this even a topic nowadays. And you might have noticed that power grid management or shortages is a recurring topic in the last 2 years, whereas 10 years ago you didn't read so much about that before. The reason or the reason why this is the case nowadays lies in the fact that we have a rapid expansion of renewables in our power grids on a national and regional level. And more than 80% of the additional power capacity that is installed each year is coming from renewables. Think of wind farms, think of photovoltaic power plants, and so on. And just to give you a ballpark number, in 2020 alone, this was 250 gigawatts that was additionally installed for renewables. So if we now go to the second part of this slide, what does renewables now, which characteristics do they bring? First of all, they have a very high volatility and fluctuation because they are not as plannable as a nuclear power plant, for example. So you always need a very good time series forecasting to anticipate what will happen. Second, you have long distance transmission. So my favorite example here is think of Germany, where you have wind parks up in the north, which let's say they generate power, and this one has to be distributed down to the south. Last but not least, the power grids themselves have an increasing electricity demand, not just, let's say, for our own personal consumption, but also when you think of mobility, especially electric cars. So altogether, things are getting more complicated. So what are now we doing inside? Are we approaching the topic of power grids? Let me. Oh, sorry, one slide too far. All these challenges are listed on the page before lead to lots of power grid instability, and the example I took here is congestion. You see this here with the red line. So you basically have one part of the power grid network where you have an oversupply of power, let's say 105 or 120%. So this might lead to overheating or even, let's say, fuses going through. And the only way to tackle this nowadays is not by fixing it within the power network via intelligent routing, but by either curtailing renewables. This means, let's say, in extreme cases, taking photovoltaic or wind turbines off the grid. Or the other option is if you have, let's say, an undersupply of power in certain stages, that you, sorry, one page back, that you buy additional energy on the stock market, or also on the spot market, to compensate for the undersupply. And this compensation typically is from fossil fuels. So this is both the cost issue and the CO2 balance issue. And just to put this into perspective, this is not the small toy problem we're here talking about. In a country like Germany or France, we're talking here about 5 to 6 billion per year, which is really wasted on congestion management. For smaller countries like, let's say, Austria, Croatia, Belgium, and so on, we still talk of a range of 250 to 500 million euros per year. This is just energy gone. What is our approach to fix this? Instead of, let's say, buying more energy outside the grid, or let's say reducing the renewables outside the grid, we developed a solution that is conducting intelligent grid or energy routing within the grid. So you can see here, to stick with this very simple example, in order to alleviate or mitigate the congestion, we subdivide the network into two smaller networks. So each of them does not have a congestion or also not an undersupply. You might rightfully ask, so what does this have to do with AI? Why you need AI for this? The example I showed on the previous page is very nice. You have like 5 power lines and 4 substations. A kid could do that is playing tic-tac-toe. In reality, power grids are very complex. So you have hundreds of substations and even more power lines connecting the substations. And the complexity is growing double exponentially in total. And to try to visualize this with this point cloud, you have 10 to the power of 100 possible switching stage in a power grid, even for a small country like Austria. So just think what this would mean if you take the United States or Germany. This is just a level of complexity that is not feasible for humans to handle. But luckily, AI to the rescue. Similarly, how reinforcement learning was used to tackle the complex game of AlphaGo or logistics. We're applying reinforcement learning for power grid management. And you see this here at the example of the Californian grid. This is where we participated in a challenge that was hosted by the French grid operator RTE. And with our approach, we received a 60% cost reduction versus traditional congestion management approaches. Plus, equally important, it also increases the robustness of the grid because you're more resilient when it comes to blackouts and so on. So much for, let's say, the good part of the story, AI for good, how to make power grids safer and especially more cost efficient and CO2 efficient. But as we've also seen in the video, the topic of the energy consumption of AI is becoming more and more important, especially as AI has switched from being a purely B2B application where, let's say, people like the audience in this webinar knows about, but let's say the vast majority of end users never heard about it. Nowadays, with tools like ChatGPT and Stable Diffusion, you have hundreds of millions of people which are using AI every day. So the question is, what does this mean now for the power consumption? I think one very often cited statistic is what you see here in front, because this is very relatable. If you compare the power consumption of a regular Google search, so let's say what is the best and most important webinar on time series, you will find this one, of course. This query is only like 0.003 kilowatt per hours. Now, if you would do the same prompt in ChatGPT, you have a power increase of a factor 1000 minimum. And mind you, this was a very trivial example I brought. If I would upload a PDF, or if this is also, let's say, a question where the ChatGPT or like the large language model has to start the internet search, this is going even up to 5,000 or 10,000. So this is, long story short, this is not efficient. First of all. Second of all, it's also not really sustainable to think that this will go on. What is equally concerning is we now already see that power consumption is very high. And if we look how the model sizes have developed and their associated power consumption for training and later for inference, we see that we are still at a rate where a doubling happens every 3 to 4 months. Nowadays, maybe every 6 to 12 months, but nevertheless, we are still in a very high growth phase, and there is no chance at the moment that this will, let's say, ebb down anytime soon. So what could be done? Google and the MIT conducted a study together in which they lay out a couple of approaches how to reduce the power hunger of models, and I would like to introduce just a couple of them. The first one is the so-called sparse models. This means that during the training phase and in the initial rollout of a product, you use a very dense model. This means, all the weights and all the connections between the different layers that you see here on the left-hand side of a neural network are still fully connected and calculated. But once you figure out which nodes are actually necessary and which weights, you start to make the model sparser and sparser. And you might have wondered why sometimes GPT is getting a bit more stupid. This often has to do with A/B testing, because they're testing how sparse can the model be made. And once a conclusion has been reached, models like GPT 3.5 Turbo or 4.5 Turbo are already a sparse version of the initially dense model. And this is also something many companies will do from now on. The other one is not so much the AI itself, but the geography where a data center is located. And this is an example of Google training the BERT language model. And as you can see, hopefully, if it's a country where lots of the power is generated by coal, like Germany, this is like the brown dash line that you see here on the upper right-hand side, the CO2 emission for training and inference is just like 7 times, or let's say 3 times as high as if it is in a country like Norway, where you have lots of renewables, or France, where you have lots of nuclear power plants. So in this case, it's similar to real estate, location matters. Last but not least, cloud and compute architecture. This is a very fresh topic, but it is also one where perhaps the most companies have a direct leverage about it. Data centers are nowadays optimized for AI workloads, be it, let's say, the architecture that you use for storage and compute, the interconnects and so on, plus the cooling and so on and so on. And by just optimizing a cloud data center for AI workloads, you get the efficiency improvement between 1.4 to 2x, which is nice by itself. And I think for most of you, you're renting in a data center anyway, so this is a very strong buying criteria. On the right-hand side, you see the hardware. And with this, I mean, we're coming from a, let's say, age where you use GPUs for most of the AI training and inference. But this is now more and more going into the direction of dedicated AI hardware. So if you think of the latest Blackwell architecture that NVIDIA has shown 2 weeks ago, here you have far more AI optimizations than there was with a regular NVIDIA GeForce 1080 6 years ago. So this again is bringing a factor of 2.5 to or 2 until 5x. Taken together, you can get the almost 10x reduction just by using the right hardware in the right data center. But since all of these, examples are on the very large scale side, I also would like to give you, let's say, one last thing on the way, because I'm sure most of you stand or sit now in front of your own laptop. Some of you are Mac users, and the question is, what now does this really mean for your own tinkering? And I found this example quite interesting. This was is Stable Diffusion. And Stable Diffusion offers you two options. Either you use it in the CPU and GPU version, like it was initially released. There you have a power consumption. You need the full power drain of 28 watts, but you're also quite fast with 2 steps per second. If you use the so-called neural engine, this is the part of the die within the newer Apple chips that is, let's say, optimized for matrix multiplications like you have in AI models like integer 4 or integer 8. You get the power consumption reduction of more than 80%. So in some cases, like 88%. The speed, of course, you have a bit of a trade-off, but the interesting thing is that the right one I could do when I wait at the airport or at the train station, I could do this for several hours. The left one, if I do this before the flight, then in the flight I can read a book, but definitely not use my Mac anymore. So what is on the horizon? Maybe a very brief outlook in the end. I talked a lot about classical silicon architectures and data centers. And yes, of course, there will be even more progress in the future. But we're also reaching the end of Moore's law. So there is now active work going on what could be the next generation of chips, especially for inference. And one of the most likely candidates here is photonic computing. In the too long didn't read version, you use interferometers to conduct the inference, and thus you get speed ups and especially power consumption reductions by several orders of magnitude. So with this, thanks a lot for having me, and I'm looking forward to the Q&A session later.
Thank you, Clemens. Name of your company is certainly your mission. You put some light on AI, definitely, and on the different aspects. That was an excellent overview of opportunities and also threats. But when we think about energy efficiency, as you also rightfully said, we can't consider AI alone. And as you can see by this kind of old analysis by Enerdata, the energy consumption of data centers was already greater than that of entire countries in 2020, and it was 3 years ago, when AI was nowhere as developed as nowadays. And so obviously many other forms of processing data cause massive energy consumption as well. And it's not just the calculation of the AI models. Interestingly, we have not yet found any studies that compare exactly this, but from what data scientists tell us, typically 80% of their work is dedicated to pre-processing the data. So in the following video, however, we want to take a closer look at exactly that and what we can do in our time series technology to use the resources we have as efficiently as possible. Let's take a look at that together. Vera, please start our video.
Hi, I'm Christian, Head of Product Development at HAKOM and Product Owner of the PowerTSM platform. My team develops the core features of our time series technology and is also responsible for operating the cloud system. Let's start with a brief overview of the different usage scenarios. Many of our customers still operate the technology themselves in their own sphere. Recently, they also have the option of storing and processing data in their cloud tenant. And this is exactly where we support them. To show how this works, I invite you to the new PowerTSM Mission Control. As we use Microsoft Azure as a hyperscale platform, the entire services are set up and monitored in the Microsoft Azure portal. The platform essentially consists of app services, database services, and virtual machines. Let's start with the app services. The PowerTSM HTTP API gives you full access to the entire functionality of the time series technology. By using vCPUs, we can scale this service in a completely flexible and demand-driven way. As you can see here, you can choose from different plans. The PowerTSM portal provides services such as login credentials, documentation, and cost monitoring. Scalability also plays a major role here. We can scale it up very efficiently on an ongoing basis with new customers, always depending on the overall usage of the service. There are a number of other services, such as automation accounts, hybrid workers, or virtual machines, but they are not relevant today. Let's continue with the database resources required to store and query time series data. To be as efficient as possible here too, database resources can be flexibly pooled for different purposes. With this in mind, we have bundled our free trials and all our low-cost level entry plans into a single elastic pool. So let's have a look at the pool settings. This is where you select the database transaction units for the entire pool. These DTUs are a metric for combinations of CPU and maximum possible read and write operations. Based on this, the 46 tenants in this pool can flexibly use between 0 and 800 DTUs. Again, we can react in line with demand if the number gradually increases. For more powerful plans, for instance PowerTSM Standard and Premium, we can select the compute tier in addition to the DTUs. Provisioned means that a certain number of database CPU cores are provided. Serverless means that the number of cores is automatically selected within a certain range, depending on the use of the database. Extra nice, here you can even select an auto-pause delay, after which the database server becomes inactive. This allows us to save system resources and costs if, for example, no resources are required at certain times, contrasting with an extreme load for other periods. This was the setup of the service. As you have seen, you can configure a lot of things flexibly and with ease. However, if problems do occur, we naturally want to identify them quickly. That is why we have a comprehensive monitoring system in place. We have set up dashboards here to give us a real-time overview of the service status at a glance. Here you can see query times, CPU usage for the services and the databases, which helps the DevOps team to recognize possible bottlenecks. Ideally, the utilization is in a normal range. But looking at this graph, there's clearly something wrong with the database utilization. Let's zoom in on that. As you can see, we can zoom directly into the respective period extremely quickly and get the necessary insights. We immediately see a list of queries, whereby those that take a long time and have been executed very often are particularly interesting. The bar chart helps us to find them very quickly. Again, just click on it and we see the query that is causing the high CPU load right away. In this specific case, our DevOps team immediately recognized that this was a suboptimal use of bulk processing time series attributes. To fix this easily, as a workaround, we can now simply allocate more resources to avoid or at least delay the bottleneck. However, in terms of cost and energy efficiency, it is much better to do a code review where we address the specific features. As you can see, the Mission Control gives us a number of ways to make your PowerTSM journey as efficient as possible. The great thing about it is that optimization not only reduces energy consumption, but of course also directly reduces consumption costs. In the end, it's a win-win situation for all of us, the users, the platform providers, and our environment. And that's why cloud computing is so important for us.
Christian, in this video, you showed us how the DevOps can optimize the way that our time series technology works, but from your experience compared to doing that merely on premises, how does that help you? And even more important, how does it help our clients in their daily work?
Sure. We are now taking on a much more responsibility, namely for the operation of the app service and the database. For us as DevOps, this is of course partly new territory. But as we have seen in the video, we also get good tools for monitoring. And we learn more about the way customers use our technologies. Also, the tools provide extremely valuable information for product development, combined with short feedback loops. Of course, we were previously also able to simulate certain constellations in test systems, but we were always one step behind. Now we can see the performance firsthand directly on the relevant use case. In addition, the communication channels are also much shorter. In the video, we have seen that we are able to get to the point very quickly. With our on-prem customers, we check step by step which component is responsible for a problem. Is it a technical issue or an issue with the way the features of our technology are being used? So various contact persons are usually involved on the customer side, and that slows down the solution process. All in all, I would say it's not just about saving money or energy. The time it takes to discover potential weaknesses can be significantly reduced compared to typical on-prem systems. But considering the situation of many of our customers, there is also another important perspective, the migration to the cloud. Only if you strictly follow a cloud-native approach, you will be able to leverage all the wonderful possibilities that cloud technologies provide. I think about the almost infinite scalability, availability, and of course, cost efficiency. Not only when we talk about processing the data, but also when we store it. Also, I think that the transition to the cloud will not work by force, but much better by making it as easy as possible. We have chosen an approach that considers all reasonable scenarios. Staying on-prem, adding some cloud features, and of course, cloud-only approaches as well. Accessing the service should be possible in exactly the same way for all of these scenarios. That way you do not have to write new code to process cloud-based data. And as a result, it will definitely increase user acceptance. Because nobody will complain if some operations suddenly run much faster because they're using highly scalable cloud-based interface. So done the right way, it should look and feel like adding unlimited elastic storage and processing services. And all of that without having the legwork of designing and operating it. And well, that wraps up my conclusions, Stefan.
Yeah, Christian, all of that sounds really good and especially promising, makes us confident that cloud services like ours can help a lot improving the overall efficiency of complex solutions. But looking into the future from what you have seen so far, what do you expect to happen? Will the transition to the cloud be even faster than the energy transition?
To be honest, there won't be the big bang. There are certainly some use cases out there that will be still done on-prem with no particular expiration date. But when we shared these new possibilities with our client base, we were surprised that some of them are willing to migrate 100% as soon as possible. But thinking about new features and possibilities, we already see that automation will be optimized massively in the near future. We are only at the beginning of a new area of cloud technologies and their evolving features. And this applies not only to AI, but also to base technologies like ours. Platform providers will get valuable insights and receive comprehensible information how they can provide their services even more efficiently. And same applies to platform users. For their part, they will get valuable input on how to set up their use cases and what costs they can expect. I personally believe that the cloud is a real use case magnet for certain tasks. This concerns to ever upscaling cases that cannot be solved on-prem in the long term. For example, smart meter or IoT-based use cases. And if you face such challenges, you better handle them in a native cloud environment. Yeah, so with that, back to you, Stefan.
Thanks for expectations, Christian. And that's also the perfect transition to our today's call to action. I've seen already some questions coming in. Please continue asking questions because right after the call to action, we will start with the Q&A. But now let's start today's call to action, Vera.
We just saw exciting applications of AI in the energy sector. We also saw that it is important not only to set up the AI model as efficiently as possible. At the same time, we need the features of modern cloud services to get the required performance at the right time. To profit from those capabilities, Let's unleash the potential of AI and our time series technology for your specific use case. We've created an efficient process to work out a clear proof of value to make this as straightforward as possible. Together with the experts from EnliteAI, we will analyze your use case and show you how to set up time series-based AI models efficiently. We have fully standardized this process so that you can take away valuable insights within just a few hours. Challenge us and contact us at powertsm@hakom.at to get more information. And now, let's start answering some questions. As always, back to you, Stefan.
There we go. As announced, for the Q&A session, the four of us are available for you now. And please, just for your information, after the official part of the webinar, we will still continue for some more 10 to 15 minutes to answer your questions. As a warm-up and to give me a chance to sort out what has come in, I will start with one question to Clemens. As AI closely and for good reasons relate to cloud computing, with the energy sector being quite conservative, what's your experience regarding cloud affinity? Is there still some reluctance or skepticism, or is that already turning? What do you think?
It's a mixed bag. So, first of all, we're talking here about critical infrastructure, and it shows in the approach of the utilities that when it comes to managing the power grid and so on, you have the highest, let's say, requirements you could think of in terms of regulation or certification. So you think of ISO 27001, this is like for beginners, and then going in the direction of NIS2. So this is getting tougher and tougher, I would say, by the year. So for these core operations, there is the strong requirement to handle this in their own data center. But all things being equal, this is nevertheless just a small portion of what the power company is doing nowadays. What we see is when it comes to customer management, let's say invoice processing, everything when in white collar, classical white collar automation, here there's a strong willingness to first of all work together with external partners, like companies specialized in document data processing and so on, and also to host this in the cloud. I think in the midterm, not in the short term, but in the midterm, once NIS2 has settled and the companies develop the operating model, I think the more complex workloads, especially on the compute side, will also be handled in the cloud, just because it's not feasible for any type of company to invest that much into compute hardware.
Okay, Clemens, thank you. Personally, I'm very confident that also with these regulations, cloud computing will fulfill them. It will be possible to fulfill them, but this needs to be shown. Let's go to the next one. What is your thought on using AI in predicting solar, wind turbines capacity planning based on demand and supply? I'm myself positive. Yes, AI can be used for that. Clemens, would you agree?
Yes, it's. I would delete the can from your answer. It is used already, but there are two things to consider here. When it comes to supply on demand forecasting, you have, let's say, weather reports and so on, which all go into very sophisticated time series models. This works. What is currently still under development is that you use this now long-term, let's say, looking back historic data and outlook, and then go into power grid planning. So for power grid planning, I think what I've shown just now in day ahead planning, the congestion management I've shown is a day ahead planning tool. You will also see this in long term, but yeah, it's to my knowledge, there are no startups specifically working on it because they are either in day ahead or real time planning. But it's just a matter of time.
Yes, thank you. One to Christian. In which cases is it still necessary to manually intervene, Christian?
One example that comes in my mind is database query and index optimization. Azure is here analyzing queries and give optimization suggestions. And this works good for simple cases, but we figured already out that with more complex cases, the suggestions are not always optimal or helpful. So here manual intervention and also deep knowledge of the technology actually is required to get the most out of it. And also sometimes we figured out that not index optimization actually solves the problem, but different usage of our technology features. So this is an area with great potential where AI can definitely help.
Okay, cool. Thank you. Another one. What is your thought on using AI in nature solutions, carbon sequestration, and e-mobility? I think pretty much the same, Clemens. Do you agree AI can be used?
Yeah, when it comes now on the demand side management, AI, there are already field trials to think of intelligent charging, for example. The same thing that happens with HVACs and air conditionings in the United States around 10 to 15 years ago with Nest, the smart thermostat. You have similar approaches nowadays to smart charging, up to using the battery in e-mobility as for primary and secondary control of a power grid. That's one thing. And of course, within the battery pack, you think of classical automotive suppliers like Continental or AVL. They have huge machine learning teams nowadays that take care of optimizing, let's say, the charging cycles and the heat distribution during the charging. This is also an AI task. The carbon answer, I actually no, I cannot really answer because I'm not so deep into the topic. How you use AI for carbon sequestering?
Yes, thanks. I mean, the potential is vast, and we work a lot with time series, and I think any case of time series modeling can be assisted by AI in our experience, and so there are basically not that many limits in our experience. Another one, I think to Clemens, what are the most common use cases bigger AI compute customers, e.g. startups, are currently exploring?
Wait, was this the bigger use cases or the bigger cloud use cases?
No, it's just generally use cases, bigger AI compute customers. Most common
Okay.
use cases.
Yeah. Currently, clear answer, large language models. I mentioned ChatGPT before, and many companies now started to experiment with fine-tuning models for their own needs. So you might have heard that Bloomberg has its own GPT model. I mean, of course, that's not like a 260 billion parameters model like GPT-4, but nevertheless, it's a big thing. It was a big project. And more companies are now experimenting with this, like banks and insurance companies, the usual suspects that have lots of text. And for them, the compute efficiency and cloud data centers are very important. And as a little bit of advantage in these industries, I mentioned this banking and insurance, that they were already, let's say, the hyperscalers are catering to this audience. They have tailor-made offerings for them, like local data centers. I'm now standing in Vienna, so if I was a bank, I could go to a data center that is let's say, located in Vienna. So this is when it comes to regulatory, let's say, security or making the boundary conditions right, they have an advantage. And I expect other industries to follow, especially for LLMs.
Cool. Thanks, Clemens. Maybe the last one in our regular time now for the Q&A. One for Thomas. Thanks for the presentation. You're welcome. Do you use specific time series databases?
Yes, we at HAKOM usually use databases, relational databases for our time series. In the cloud, we use the Azure SQL, but we also support other specific time series databases. So we have an architecture where we can add additional connectors to different databases, and we also connect various data sources and also proprietary data sources where the time series are stored in some on-prem or cloud system, which is just not only a time series database, but time series within a system that the customer also needs to read and get into their system for some calculations.
Okay, Thomas, yes, I might add the what we call polyglot persistence. That's the specific yes way to call it for our technology. Well, now as we a bit over time now already. I suggest we stop here with the official part of our webinar, but please, for those who still have time, and we have a lot of questions still to answer, we'll go on for doing so for another 10 to 15 minutes. And for those who do not stay and we have to say goodbye to, have a great springtime. Please do also subscribe to our next webinar, which will be on data security and protection. And obviously, we will give it a very strong time series flavor once again. We will start sending out the invites very soon, so stay tuned to us. And do not forget, life's a time series. So, welcome back again. We have an interesting question. We thought about doing a survey on that, I have to say. From an energy consumption perspective, what are the ratios for data pre-processing, pre-training of models, fine-tuning, and others? It's an excellent question. As I said in this one slide of the presentation, data pre-processing itself takes for maybe 80% of the whole work you do with data when you model basically anything. So my guess would be that data pre-processing has a very high ratio. Clemens, what do you think? Do you have a better guess or another guess?
I have a very smart answer. It depends. Now I'm just the discussion reminds me a little bit of the efficiency of electric vehicles. And there are two ways how you measure this. Tank to wheel. This means, the efficiency once you have the fully charged electric vehicle and how much CO2 output do you have. Or the other one is called well to wheel. And well to wheel means you also take into account how was the power generated and in which country and how is the power mix and so on. And I think currently, to my knowledge, we don't have a similar established logic to do this. We know this from the timing perspective, where I fully agree 80% is data pre-processing. That's like the golden number, you could say, or Pareto principle at work.
No wrong.
But for pre-processing, let me give you an example. Besides power grid management, we are also processing. We have a second product that is analyzing mobile mapping data. Think of Street View analytics. Here, the pre-processing is tremendously complicated because you do stitching up to millions of different images and you merge and fuse this with LiDAR point cloud data. So there, I would say our consumption is above 80%. Now, from the power grid simulations and so on, yes, perhaps rather 50% and not 80%, because the power grid simulation environments, they are difficult to build, but they are not so energy intensive to build.
Yeah. But it's interesting. We will do a survey in LinkedIn the next weeks, and I'm really excited about what you think. Another interesting one, again, referring AI and capabilities. Do you have positive experiences in which AI can help electrical systems to cope with specific conditions that have occurred in recent years, specifically in the past few days, when we have a large production of electricity and as a result, a negative price of electricity on stock market? I'm not quite sure if the use case you presented, Clemens, it's got to do much with that.
No, I mean, in general, you have a very large and healthy ecosystem when it comes to energy trading. So the companies that are specialized on energy trading, especially on the spot market, to either for hedging or to take advantage of the situations you described in the questions, there are a couple of them and they earn lots of money because if it works, you're immediately cash flow positive. But this is basically all I have to add as an answer here.
True. There's a lot of questions, and I have to say we have to answer them in the future, maybe individually. I have recorded them, and we will come back to you. But maybe, yes, another one. Please share practical examples of AI implemented in power system operation. I'm not quite sure if I can answer it, but I will give it a try. We are in forecasting for many years now, almost decades, and we are using algorithms which are AI-based since the beginning almost for consumption of energy, for in any form power, district heat, gas, and so on, but also for production of energy, also from wind turbines, also renewables. So that, I guess, there's a lot of examples, and there will be also a lot of examples in optimization of power plants, I'm sure. Anybody wants to add something to this?
Yes, unsolicited reply. What we realized is, because let's say we don't have decades of experience in the power industry, so quite often we are invited to pitching at startup competitions, from corporate venture capital or from power companies. And the way they structure this is they have long-term planning. So this is, for example, the question before: could you use it for grid planning? Then you have day ahead planning. This is where we are, but where you also have other, let's say, could be service deployment forecasts and so on. And then you have real-time operations. This is, let's say, one of the ways our companies frame it and how they allocate use cases for it. In general, there is the movement in Europe at the moment. It's called Control Room of the Future. Many large TSOs and DSOs are working on that, and the vision is that you have far more automation within the control room. So not just the perfect simulation that is giving you the status quo and so on, but also more, let's say, anticipating what could go wrong, and then proactively making measures to basically avoid that you need they had countermeasures in the first place.
Okay, I have another one, maybe in the direction of Thomas, because I think it's about high time resolution. When faults occur in electrical networks, these are reported by high time resolution data, recording of voltages and currents. How can AI be used for analyzing this? We have an interesting R&D project we've finished quite recently. Thomas?
Yes, that's about to analyze hydro turbines, and we record data up to 100,000 hertz. So that's a very high resolution. But regarding the power supply, I think that the high resolutions are not necessary, but the high resolutions are necessary to be able to react very fast. Our time series technology is able to record this and to use this data in real time. But we don't have any algorithms in place regarding or using some AI to exploit this data and react accordingly fast. I think this would be some additional research necessary to get some algorithms that are enough fast to get results from this data.
Maybe some features of our technology might be useful for aggregating the data to make it more digestible for the algorithms. We've done this recently also, digesting data coming in second increment, aggregating it to minute or 15-minute increment, and then starting an algorithm on top of that. And then I have to say, like that counts for basically all models, not only AI. You have the validation phase or training phase, where you have to digest a lot of data, but during operations you will just run the model itself. So that makes the thing also a lot easier, even when you have high resolution data.
What we also did or do in this project is to find out some correlations between high resolution data and the low resolution data. So then during operation you could use the low resolution data to get some forecasts out of this easier to handle data in time for seeing the event in advance.
Okay, I think that wraps it up. Another interesting one, what's your feeling how fast old-school AI clients will switch from on-prem to cloud AI deployments? I have an interesting story to tell with one of our clients that we recently converted to cloud technologies. When we presented an offer and the new possibilities and some details, we were quite impressed, and also costs seemed to be quite reasonable. And then when we were all through, they once again asked, and we do not have to run a single server. And the answer was yes, yes, you do not have to. Yes, I think there will be some fast movers, obviously, especially when it's about new use cases. To migrate the old use cases is a challenge, definitely. So we will have the whole range, I guess. But there are definitely some fast movers out there. And I would say in our client base, it's about maybe 10 to 20%, I'd say, which want to move fast and also start up very fast.
I see AI as a driver to go to the cloud. For example, as you see the Microsoft Copilot, that's only available in the cloud because it's important for the assistant that he has access to all your data via the API. And I think most of the AI algorithms will only be running in the cloud on one hand for the resources that are needed for this, on the other hand for all the data that has to be accessible, and that's much easier to get up and running in the cloud than on-prem.
True. Maybe another one for Clemens, facing multiple crises. As being responsible for AI startups, do you see a certain reluctance on the part of the investors? I guess investing in AI startups.
Yeah, I think the narrative is changing a lot. I think I once mentioned before during my slides that 5 years ago AI was a pure P2P play. So you do banking software or solar forecasting, and nowadays it's a consumer play. So what has this to do with the investment world? The theory back then was 5 years ago, almost all founding teams of AI startups would look very similar. You would have 2 or 3 people with a PhD or master degree in something like applied mathematics, statistics, and so on. You know, the complicated stuff. The people developing the models, and then a couple of co-founders either coming from the verticals or from the domain and from the business side. Back then, the premise was that you're only an AI company if you develop fully your own models, and this is the moat, means the defensibility that you create. Nowadays, the narrative has shifted because you have this explosion of open source models, and I think it reminds me a little bit of the Web 2.0 era when companies like Uber or B&B were started, and you had very strong open source networks and technologies where these companies were built upon. Nowadays, there is a high reluctance to invest in startups that just have great technology, and the business aspect is nowadays far more, let's say, important than it was 5 years ago. 5 years ago, the people thought, oh, this is like a bunch of people like in the pharmaceutical industry that will come up with a model that nobody else can replicate, and they will figure out how to make money. Nowadays, if you raise money, you have to show how you will earn this money back and use as much open source as possible. So it became more normal, so to speak. The only outlier is if it's something where there are no good open source models available. Think of, let's say, material science, or I think life science is also a very good example, or where it's incredibly costly to train a specific model for an application. So for large language models, you still have companies that are doing this from scratch, but the number has decreased compared to the boom from last year.
Okay, thanks for your insights. How is HAKOM operational in providing AI services globally for energy and power consumption? For our time series technology, our technology is an enabler. So what we offer is a cloud service that is very useful to do a lot of this pre-processing that we talked about, as well as validation, and then obviously also afterwards deploying the results and doing whatever you want to do with the results. So that's basically our job. And in that sense, we are open to any kind of AI that runs on top of our technology or using our technology. And this is exactly also what we envisage in our cooperation with EnliteAI. I think cooperation is always necessary and very useful. Remember the 80% that the data preprocessing takes and the legwork and headache it gives to get a sound database. Clemens, something to add? We would like to do this together, wouldn't we?
Yeah, of course. I mean, I was just smiling because in general, it's interesting how rarely you meet direct competition in the AI space. Most of the time, it's synergetic. I mean, in our case, it's the perfect handover. But I even see this in other areas because startups, yes, in their pitch deck or on their homepage, they pretend that they serve the world and all use cases that could ever exist in a domain. But more often than not, they serve a specific niche. And very rarely you have two companies serving the same niche.
Cool. Another interesting one, is AI able to answer future power consumption levels? Well, I think like from any kind of algorithm or models, you must not expect miracles. I mean, if it's in the data, it's there, and AI is most likely to find out. And AI is very powerful, but still, everything you want to know needs to be in the data first. So it's a yes but answer. Clemens, anything to add? It's especially is AI able to answer future power consumption levels? So very general question and very
I would put the asterisk there. Yes, but not AI alone. It's rather if you talk with people that are, let's say, professionals when it comes to creating economic models, power consumption models, traffic scenarios, and so on. In these disciplines, you have a model, or let's say a method mix since decades, ranging back to decades, and AI, let's say, is just the latest method you put into the mix. But to my knowledge, no one would, let's say, disregard what happened before and then go all in AI. This is not how these disciplines normally work, because you also need to be able to still keep the comparability with what you did 5 or 10 years ago.
Yes, and domain knowledge will help in any case. so like always. Another one to Thomas, maybe. I don't know if we have tried or managed to couple time series and graph approaches. Did we?
No, up to now we did not try how to combine graph databases with our time series solution. But it's an interesting question to see where the advantages of graph databases are useful for our time series databases, especially for the master data. I think this could be very interesting to build up some graph to see which time series are related to another time series, and to exploit this via time series graph databases.
Cool. So our time is 25 minutes or even more. So I'm afraid we have to finish now, but thanks to all of you in the panel for answering the questions. Clemens, to be with us today. And I hope we see you soon again. And once again, don't you forget, life is a time series. Bye-bye. And yes, as a follow-up, we will answer all of the questions that are still open. I must not forget. And we will not forget. Bye.
Thank you. Bye.
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 Bye.